All right, today we're diving deep into the very fabric of reality to take a closer look at a cornerstone of modern physics, the space-time diagram. But what if that tool, this thing we've been using for over 100 years, is built on a really simple, fundamental flaw? Well, that's the wild idea we're going to dig into today.
So what are you even looking at here? This is a pretty radical reimagining of a space-time map. You can just forget those flat, kind of boring diagrams you might remember from a physics textbook. This is a dynamic, multi-layered model built with 3D software, and it's at the heart of this argument that maybe, just maybe, we've been visualizing the universe all wrong for a century.
So this gets us to the big question, the whole point of this explainer. The author of our source material is posing a really bold challenge. Is the standard Minkowski diagram, the bedrock of special relativity for 100 years, actually misleading us?
To really get why someone would challenge this, we first need to understand what we're even talking about. What is the standard model, and where, according to our source, does it go wrong?
Okay, if you've ever taken a physics class, this thing right here probably looks super familiar. This is the classic Minkowski diagram. And its beauty is really in its simplicity, right? You've got a horizontal axis for space, a vertical axis for time, and together they create this clean, two-dimensional grid where you can plot events.
So what does it do? Well, at its core, it's a tool for visualizing how events unfold in the universe, all according to special relativity. See, an event isn't just a place, it's a place at a specific time. This diagram is supposed to be our map to that reality, but according to our source, this guide has been leading us down the wrong path. The author behind this whole argument, from the blog Ziana 2023, actually has a pretty interesting name for this problem: mathematics infatuation. The claim is that the people who created this model were so in love with how elegant their equations were that they completely overlooked a basic fact about how we actually see the universe. And this is where things get, well, really spicy. The author claims that brilliant minds like Lorentz and Einstein made a simple mistake. They created this perfect, abstract mathematical world, but then treated it like it was the real world. And in doing that, they forgot one huge real-world detail: the time it takes for light, and therefore information, to travel from an event to whoever is watching it. So, okay, if the old model is broken, what's the fix? This is where our source suggests a major paradigm shift. We need, they argue, a totally new frame of reference. We need a new umpire to call the shots. The old way of thinking? It's all about your point of view. Your map of spacetime literally changes depending on your motion, like are you on the moving train or are you standing still on the platform? But this new idea? It says, forget all that. Let's use one single, absolute, non-moving frame of reference: Maxwell's electromagnetic field. The fundamental stage where light itself performs. Now, to make this whole thing click, the author uses this brilliant analogy. Think of a tennis match at Wimbledon. The moving train is player 1. The observer on the tracks is player 2. Each of them has their own, totally subjective view of the game. But who has the objective, true perspective? The umpire. In this analogy, the umpire is Maxwell's electromagnetic field, the absolute, impartial stage where all the action really happens. So what's the big takeaway here? It's this: the author proposes we get rid of player 2, the relative observer, from the equation entirely. Instead of trying to map reality from their biased point of view, we should be mapping it from the umpire's impartial one. It's a huge shift from a relative to an absolute way of describing things. Okay, so what does a space-time diagram actually look like when we use the umpire's view and, actually account for the physics of how we see things? Our source uses some pretty cool modern tools to give us a peek. All right, we're back to this crazy 3D model built in Blender. Now, look closely. See that blue ball at the bottom? That's not just a decoration. The author calls it the camera eye, and it is the absolute key to their entire new approach. It represents the actual, physical location of an observer in 3D space. So this camera eye is the proposed fix for that simple mistake we were talking about earlier. By giving the observer a physical location in space, the model has to account for something called information delay. An event that happens way over there isn't seen instantly. The light from that event has to travel all the way to the camera eye, and that travel time is now built right into the diagram. Okay, so how do you build this thing? It's actually a pretty straightforward three-step process. First, you set up the umpire's absolute grid. Second, you place your observer, the camera eye, at a specific spot. And third, you plot the event. But here's the game changer. If an event happens at the origin at time 0, and our camera is 10 light seconds away,
We don't see that event until time equals 10. The map now reflects the actual physical process of observation.
So, what does this all mean? What are the bigger implications of looking at the universe this way? What happens when we choose to model physical reality over just pure mathematical beauty?
And wow, this side-by-side really just says it all, doesn't it? On the left, you've got the classic Minkowski diagram. It's abstract, elegant, and flat. On the right, you have the author's Blender model. It's complex, it's a bit messy, and it's grounded in 3D space because it has to account for where the observer is. One is a mathematical ideal. The other is an attempt to model physical reality, warts and all.
And that really gets us to the core of this whole argument. It's kind of like a cautionary tale for all of science. The beautiful song of mathematical elegance can sometimes pull us away from physical reality. If our models ignore fundamental rules, like the speed of light and information delay, they risk becoming nothing more than just pretty but ultimately useless puzzles.
In the end, this whole exploration leaves us with a question that's way bigger than just physics, right? It's a classic philosophical problem that our source brings right to the front. How do we make sure our scientific maps don't cause us to lose sight of the actual territory? And what other beautiful maps out there might be leading us astray?